Model Context Protocol, or MCP, is like the USB-C, or Universal Connector for AI applications. Let us try to explain what that means. MCP simplifies and standardizes how your applications, powered by LLMs, interact with services, tools, and even data. LLMs excel at understanding context and generating responses accordingly. They're just next word predictors. They can write emails, but they can't send them. In our existing digital ecosystem, we have systems or tools that can perform actions. For example, email management to send an email. Email management systems can be instructed by LLMs to send these emails. However, as the number of LLM-powered applications grows, so does the complexity in how they interact with external tools, whether it's databases, APIs, or other systems. Currently, many of these applications rely on their own custom ways of talking to tools. This fragmented approach is not only inefficient, but also hard to maintain and scale. Imagine if every computer in a network had to use a completely different communication method to talk to every other machine. Chaos would be inevitable. That's exactly the kind of inefficiency we're seeing in the way different LLM ecosystems are evolving. MCP, Model Context Protocol, a promising open standard, can be a game changer for how language models interact with external tools. With MCP, developers can define a common interface for tool communication, bringing much needed order to the diverse and often inconsistent methods used today. MCP can be compared to REST for the web. REST brought in a simple, standardized way for clients and servers to talk and transform the web. MCP aims to do the same for AI ecosystems. Once widely adopted, MCP will allow new clients to interact with tools in a consistent manner, and tool servers will have the power to define roles, access levels, and capabilities, all within a unified structure. It's a step forward, building a more scalable, secure, and interoperable AI infrastructure. MCP redefines AI integration by addressing inefficiencies inherent to traditional APIs. Imagine traditional APIs as a box of mismatched power adapters. Each AI model requires custom code to connect to external tools or data sources, akin to hunting for the right adapter each time. This fragmented approach creates an M by N problem. Connecting M models to N data sources demands M by N unique integrations, a costly and very time-consuming process. MCP standardizes these connections. Instead of custom code, AI systems use a single protocol to interface with APIs, databases, or tools. This eliminates redundant development work and ensures seamless interoperability. For example, a weather app using traditional APIs would need separate integrations for various models, from OpenAI, say GPT-4o, or Gemma 3 from Gemini. But with MCP, both models access the same standardized interface. Some of the key differences and advantages include interoperability. MCP's open standard allows diverse AI models such as OpenAI series models or series models from Anthropic or Google to share tools and data without re-engineering. Real-time context. Unlike static API calls, MCP dynamically pulls context, for example, live data or user preferences, enabling richer and adaptive responses. Security. MCP embeds user control, letting individuals dictate data access and a contrast to opaque API permissions. While MCP reduces complexity, its success hinges on industry-wide adoption. Early supporters like Block, Apollo, and tech giants like OpenAI and Google signal momentum, but legacy systems reliant on custom APIs may face migration hurdles. In essence, MCP isn't just an upgrade, it's a foundational shift toward an open, efficient AI ecosystem, much like USB-C replaced proprietary chargers. Its ability to future-proof integrations while prioritizing security makes it a compelling successor to traditional APIs.